Let's talk about alkenes in Br2. We just talked about alkenes plus HBr. Now let's talk about alkenes and Br2. Once again, I thought we covered this already, right? So alkenes plus Br2, if there's no light, go through this bromonium ion that's then opened up into this dibromide, which we know is going to be trans every time. Okay? But what if we have some radical initiating in there, so some light, let's say, and we're able to get some bromine radical, right? So bromine, let's say we've got bromine, quite a bit of Br2, some alkene, and just the tiniest bit of Br dot. Okay, two things could happen. One would actually give us kind of the same product, right? So this radical could add into the pi bond, kind of like we saw last time. We'd end up with this bromine here and this radical here. And again, if we don't assume it's going to happen with termination, then we'll just say, oh yeah, this radical will find some other molecule of Br2. We'll end up with this dibromine plus Br dot, which will then enter the catalytic cycle. But that's not the only thing that could happen. Turns out something else could happen. So what if instead of adding into the pi bond, we actually broke this CH bond, right, and did hydrogen abstraction? It would seem like a tall order for hydrogen to do this, but again, this isn't any different than the alkane step. And remember that this is resonance stabilized. Right, it can spread out this odd electron over both carbons. So this radical abstraction is actually pretty easy, and as we'll see later, pretty biologically important too. So if we do this, now that radical can react with bromine, and we actually end up with a brominated product where our alkene survives, and we're brominating next to that pi bond. And so we're going to call that allylic bromination, right? Allylic is the site that's next to a double bond. So allylic bromination. For the same mechanism, we could imagine having a methyl benzene or a toluene, and then if I give this dibromine and light, it wouldn't go through the electrophilic aromatic substitution stuff that we saw earlier. Actually, we'd go through the radical here. We'd do hydrogen abstraction. We'd get the radical, which would then add just like this does. So benzylic bromination and allylic bromination go by the same way. So we got a react off, right? So I've got two different routes here. How do I know which one of these it's going to pick? Well, once again, like always, we get back to kinetic versus thermodynamic. This one is kinetic. So that pi bond that I'm breaking is really quite a bit weaker than a sigma bond. But it's pretty easy for this to just go backwards, right? This can just kick out Br dot to go back to the pi bond. It's much tougher for this one to go backwards because as soon as I generate this and I make HBr, HBr leaves. And if this radical is like, hey, I want to go backwards, where'd that HBr go? This HBr is gone. It is gone. Okay? So this step, it might be slower. It might not be the kinetic product, but once I do it, it's essentially irreversible. And so as long as I keep my amounts of radical low, right, so this step is slow, as long as I keep my amounts of bromine low, maybe add it very slowly, it's actually pretty straightforward to me to do this. So we just saw a lot of competing reactions there, right? So alkenes can react with HBr, they can react with Br2. So how can we select for allylic bromination and not just get normal old weak one alkenes plus HBr or alkenes plus Br2? So one way is to make sure that the concentration of HBr and Br2 is always really low. And the way we're going to do that is with something called NBS, N-bromosuccinimide. That's this stuff. N-bromosuccinimide is a molecule. First of all, it's a really nice, safe, and easy to use source of Br plus, essentially electrophilic bromine. But really, its job here is to turn HBr into Br2. Right? So HBr reacts with NBS to give Br2 and just succinimide byproduct. Okay? So how's that going to help us? So here we go. We're going to start with NBS. And honestly, it works a little bit better if the NBS is a little bit impure because that impurity is just a trace amount of bromine, Br2, that can help to kickstart our catalytic cycle. So this is kind of the one beautiful crystalline thing that we will not recrystallize because a little dirty is okay. Radical initiator. So we want to make sure this goes under radical mechanism and not just the normal nucleophile stuff. And so we're going to give it light and some initiator. That initiator could be peroxide, or oftentimes it's this AIBN stuff, which is just, again, a molecule that blows up real good. It loses N2 in the middle there. It gives me two nice stable radicals. The structure of the radical initiator isn't super important. It just gives us radicals that then starts our chain reaction. Okay, so I take my alkene and NBS and some radical initiator, shine a light on it. I'm going to get a little bit of bromine radical. Again, probably from that little bit of impurity bromine that's on the crystal. That radical is going to take a hydrogen from this allylic position. Again, there's not a whole lot of bromine around. So we'll do that. Once we get this radical, now this radical, well, first of all, I'll get this radical and HBr. And as soon as I make HBr, my NBS reagent turns that HBr into Br2, only as much as I need. And then that Br2 reacts with that radical to give me this stuff and some other bromine radical that then goes and restarts my catalytic cycle. Okay, so all of this is kind of a nice, turn the crank catalytic system. I don't need to have a big supply of bromine 2 or HBr in the pot because NBS is kind of helping me flip back and forth between to get the one I need. And so this is a really nice, gentle, high-yielding way for me to do allylic and benzylic bromination, which I'll remind you is pretty cool, right? So we've done lots of reactions with alkenes, but we always react at the pi bond. And this is the first time that we're actually reacting using the pi bond to react next to it. And now this thing can not only do Grignard reagents and SN2 reactions, but once I do that, now I still have an alkene that I can do all those kind of alkene reactions with too. So being able to do allylic and benzylic bromination actually is a pretty useful little thing we're able to do.